Hi and welcome to video 13, Unit 4, Topic 1, Math Methods Curriculum. In this video I'm going to run through some theoretical optimization questions. So there's two in this video and then one in the next video, and then we'll move on to some other context. So let's begin. Part A. Find the point on the line y equals 4x plus 7 that is closest to the origin. Now we'll start with part A here, and I will just recognize here that when I sketch this, there is another way of doing it, which I'll talk about briefly. But let's first start by sketching. This is our step one of the optimization process, building an understanding of what's happening. So first of all, 4x plus 7, well, it has a y-intercept at 7, so I've got a scale there of each line equals 2, and it's also got a gradient of 4, so it's quite steep like this, and that also means it goes down like this. So there's my straight line function. It's not perfect. I don't need it to be perfect because we're going to do this question algebraically. And what I'm saying is that there's some point here, P, X, Y, such that that is the shortest distance to the origin. That's what the question is saying. Now it turns out that that point will be also perpendicular to the original line. So what I could do is I could find a line that goes through the origin and has a gradient that's perpendicular to that straight line, and then I could find the point on the line where they meet using simultaneous equations. So there is another way we could do this question, but I'm going to do it using optimization. So what we're trying to do is to minimize the distance between P and O, the origin. So we want to minimize D, and if you recall, the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. That's the distance formula between two Cartesian points. But if you don't recall that, remember that distance formula is really just a bit of Pythagoras. If I use a bit of orange here, so this gap here, this is x2 and this is x1, and this is y2 and this is y1, and we get the differences here, and then we use Pythagoras theorem in that right angle triangle. So the distance formula is just a rearrangement of Pythagoras theorem. You could probably get there with that distance formula. Anyway, in this case, we know that P is point x comma y, and O is point 0 comma 0. So therefore, the distance formula will be equal to the square root of x minus 0 squared plus y minus 0 squared. And this, of course, is the square root of x squared plus y squared. And so that's a good start. But the issue we've got is that we don't want, or we can't minimize or maximize in a situation where D is a function of x and y. So instead we need to find another representation or relationship between x and y. That means that we could substitute out x or y, and D will be in terms of x or y only. And here it is. We know that that point lies on this line, so that relationship must hold. So we also know that y is equal to 2x plus 7. So just to remind you through the steps, step 1 is this, that's getting an idea of what's going on. Step 2 is building our relationships and defining our key variables, in this case point x and y. And then step 3 is solving simultaneously to get to a single function in terms of one other thing. And I'm going to do that now. D is equal to the square root of x squared plus, so that should be a 4, shouldn't it? Probably wondering what I've done there. 4x plus 7 squared. And so there's my solution. Now the question does say find the point, so we're actually looking for P, not D. But we're going to minimize D. It will give us an x where D is the minimum, and then we can put that in for y, and it will give us the point. Okay, so D is equal to this. Then dd dx. Sadly, the notation dd is avoidable, and I haven't avoided it, so maybe be considerate of using d as a variable. And dd dx is the derivative of this thing here. Now I probably need to actually just show another step here and simplify one more step. So square root of x squared plus 16x squared plus 56x, that's 4 times 7 times 2, binomial expansion, plus 49, and that's equal to, and I might even write it as a half function, x squared plus 17x squared plus 56x plus 49 to the power of a half. And now I can derive that. dd dx is equal to the derivative of this, which is a half, times the original function, 56x plus 49 to the power of negative a half, decrease it by 1 in the power, multiplied by the derivative of the inside function, and I'll do this in full. So I'm deriving ddx of 17x squared plus 56x plus 49. That's equal to a half times 17x squared plus 56x plus 49 to the power of negative a half times by 34x plus 56. And now rewriting out in full, turns out the 34 and 56 have got a factor of 2. That makes that 17. That makes this one 28. And I can write this down as 17x plus 28 all over the square root of this stuff. 17x squared plus 56x plus 49. And that's my dd dx. And now I want to simplify this, so I'm going to let dd dx equals 0 to solve and find the stationary point. So I get 0 is equal to this, 17x plus 28 over the square root of 17x squared plus 56x plus 49. Now this is where the magic happens, and this will happen in quite a few different contexts. Notice here I've got something on top and something on the bottom. Now to make this thing 0, this is like an alternate version of the null factor theorem. The only way I can make this thing 0 is if the numerator is 0. If the denominator equals 0, I've got a big problem because we can't divide by 0. And there's no other value the denominator can take that will make this thing 0. So what I'm going to do is, and a good mathematician here would make the statement that that cannot equal 0, otherwise we've got a big problem. And instead, I'm going to say, well, the only way to make this 0 is to have the numerator equal to 0. Or maybe I could multiply the denominator off as well as another option. So 17x plus 28 is equal to 0, and therefore 17x equals negative 28, and therefore x is equal to negative 28 over 17. Which is a weird number. It's less than 2 but more than 1. If I go back up to the original function though, I am expecting x to be negative, and it is negative, so that's a bonus. There's my x value, and you'll recall that y is equal to 4x plus 7, and 4x plus 7 is equal to 4 times negative 28 over 17 plus 7. Whatever that is, I'll tell you it's 7 over 17. And so p x comma y is equal to negative 28 over 17 comma 7 over 17. Now I did have to, so this is me getting the overall point, getting the final point here. So that's my step 6. I haven't done step 5, so I do just need to check the nature of that stationary point. And again, I would probably check the nature, because it's a complex function with a square root, I would check the nature d and x and d dash by considering negative 28 over 17, and then considering one below, which is negative 2, and one above, negative 1. And I should get, because this is a minimum, I should get a negative gradient, 0 gradient, and a positive gradient, giving me negative 0 positive. Or you could also plot this function, the original function here, to prove it's a negative. Or do the second derivative if you're a little bit crazy. Okay, let's look at part B. So in part B, find the points on the hyperbola, and my apologies, that shouldn't say hyperbola, that should say quadratic. Find the points on the quadratic y equals x squared minus x plus 1 that are closest to the point 1, 0. So I'm going to do part B over here. In fact, I'm going to take that across a little bit more, and we'll move across and we'll do some of our work here. So in part B, we're dealing with this quadratic, y equals x squared. It's a similar question. I did originally have a hyperbola, but I changed it to a quadratic. And I forgot to change the word, of course. Similar question, but the point has changed from the origin now. So this particular quadratic looks a little bit like this. It doesn't go below the x-axis and has no x-intercepts. And there's some point, this is 1, 0, and then we'll define this point here as p x, y again, and we want to minimize this distance. So again, we use that distance formula. It's a very similar process. This time I might not use d, so I don't fall into the dd trap, and instead I'll use the distance as a. So let's say a, this distance here, is equal to the square root of x minus 1, remember it's x2 minus x1 squared, plus y minus 0 squared. That should say squared. So I've got x minus 1, y minus 0 there. And this is equal to the square root of, I'm going to expand, x squared minus 2x plus 1 plus y squared. And now I'm going to go back up to the other relationship and make the statement, well, we know that y is equal to x squared minus x plus 1. And therefore y squared is equal to x squared minus x plus 1 times by x squared minus x plus 1. And I can expand and solve this and then put it in. So I get x to the power of 4. It's a bit crazy. I get 2x cubed. I get an x squared there, an x squared there, but I get a negative, oh no, another positive x squared. So I get 3x squared. I get 2 negative x's. And then I get plus 1. So there's my expansion, and now I'm going to use that expansion back into the original function. So I get my a, my distance, is equal to the square root of x squared minus 2x plus 1 plus y squared, which is x to the 4 minus 2x cubed plus 3x squared minus 2x plus 1. So things are a little bit out of hand here. And this is equal to the square root of, I'll put the x to the power of 4 first, minus 2x cubed plus 4x squared, which is the 3 and the 1 there, minus 4x, which is the negative 2 and the negative 2 there, plus 2, and that's my final a value. And of course, it's probably best here to write this as a half power, 4x plus 2 to the power of a half. So there's my a. Now I'm going to derive that, so I get a dash is equal to a half x4 minus 2x cubed plus 4x squared minus 4x plus 2 to the power of negative a half times by the derivative of the inside, which is 4x cubed minus 6x squared plus 8x minus 4. And you recall that this brings me out to this again. Now, first of all, that half and this 4 becomes 2, 6 becomes 3, 8 becomes 4, 4 becomes 2. That half there, so often it cancels out with stuff. So look for that opportunity. Not always though, but often it does. And I get 2x cubed minus 3x squared plus 4x minus 2 all over the square root of this other stuff, x to the 4 minus 2x cubed 4x squared minus 4x plus 2. And that's my a dash. Now we're at that point again where I'm going to let a dash equal 0, so I'll have 0 here, and we're at that sort of null factor point. This must be 0. It's the only way to make this whole thing 0 is if the numerator is 0, and so I get therefore 2x cubed minus 3x squared plus 4x minus 2 equals 0. It's a cubic with no hints on how to solve it, so there's an expectation here that you would be welcome to use your calculator, and I get this. X is equal to 0.694. I got that from my graphics calculator, but you notice here it's a cubic, so a cubic could have one solution, maybe 3 solutions, and maybe it could have 2 solutions where it just touches and it goes off. So probably 1 or 3 though. In this case we've got 1, so we're happy that it's only got 1 solution. That works. And that one solution, if we do a gradient table test for it on a dash, so we've got x and a dash, If x is 0.694, we get a dash is 0. If x is 0, we get a negative. If x is 1, we get a positive. You can also do this quite cleverly in your calculator, giving us that, and therefore it's a minimum. And of course, we need to get the coordinate. So at x equals 0.694, y is equal to 0.7876. Because remember, y is equal to x squared minus x plus 1. And the shortest or the closest point to that coordinate 1, 0 is 0.694, 0.7876. And if I go back to my graph, which is pretty rough anyway, but I can see I was kind of expecting that, so it's about here. All the best.